We will wait for 5 more minutes in case there are more people who want to join. Can those who are here, can you hear me? Is my voice audible? You can put a thumbs up or react in the chat or something. Okay, thanks. And you can see my screen, right? You can see my screen, I hope. Okay, in case I am not able to see the chat, please also respond by unmuting. But yeah, we'll wait for 5 more minutes in case more people want to join. I'll just share my screen. Okay, we'll just wait 2 more minutes in case more. I can see more people are joining. So 6:05 we'll start the class. By the way, sorry that it had to be on Saturday evening. I had a unavoidable prior thing on Monday, so that's why the next class will be on Monday only. So yeah, so Mondays are the regular class. Only this week I had to change it for this reason. I hope you are all able to hear me. My voice is clear and all that. Just put a react if you can hear me. Hello, am I audible? Okay, I am assuming I'm audible because before it was someone had said. Okay, one second. Okay, there is some message in the chat. Let me try to see it. Uh, Hi ma'am, before we start, can you answer what is the real color of the sun? If white, then why is it always portrayed as yellow ball of fire in textbooks and pictures? So, right. So, if you recall in the last class, we discussed about how stars are like black bodies, right? In the sense that like a black body, they emit in actually all the wavelengths. So in a sense, the sun emits in all wavelengths. So what we get from the sun is actually somewhat like white light, because all the colors are mixed together. And not only it emits white light and visible range, but as you saw last time, there's an electromagnetic spectrum. So it actually emits in all the wavelengths of light. Now every black body spectrum is peaked at some value, and that value for the sun happens to be the yellow color. And in fact, last time I gave you an exercise that you can try, which is that using the yellow color of the sun, you can estimate how much should be the temperature of the sun. So actually we can't say that the sun is this color or that color. The what is the real color of the sun, it depends, right? The reason we see the sun like yellow is because white light, all the wavelengths of light are coming to us, but so, some of the light is getting scattered, and eventually what we see is blue, yellow color, right? So if you calculate based on the black body spectrum, you will find that it peaks at the yellow color. So that's why maybe we call sun to be yellow color. Does that answer your question? So sun and all the stars, they emit in all the wavelengths. That's why last time I was talking about this multi-messenger kind of thing, where we have to send not only optical telescopes, but we have X-ray telescopes, we have radio telescope, we have different kinds of telescopes, because from space we actually get signal from all across the electromagnetic spectrum. So that is a very important point to keep in mind when we look at the sun. And last time actually, if you look at the slides, I had included one slide which was the picture of the sun in different wavelengths, right? How the sun looks like in one wavelength is different from how the sun looks like in another wavelength. So it's a little, of course we all grow up saying the sun is yellow, and it looks to be yellow with us because by the all the things that I mentioned, like the scattering of the light, and where the black body spectrum of the sun peaks, we eventually see it as yellow. But there are lots of wavelengths which our human eye can't see, which is also being emitted by our sun. So color, temperature, these are things that that we use to get a feel for things, but not necessary that you know that is, if I say sun is yellow, it does not mean that the sun is only emitting yellow light. All stars are emitting at all wavelengths is the assumption that we make when we say that stars behave as black bodies. So that is kind of what I was trying to say last time. This problem solving session is for week 2. As was communicated to you, I had a prior commitment for Monday's class. So every week you will have for every that corresponding week. So the week 3 class will go on Monday as is per the schedule. The week 2 class I was not able to take on Monday because I had a conference and I had to be there, a prior meeting. So that is why we will be having our week 2 class today. The other weeks will go as planned. Okay, I think we can start the session because and people can join in. It's already 6:08. So yeah, so I think you can all see my screen and you can hear me because I can see people in the chat are responding. So yeah, so for anyone who's joining for the first time, we already had one of these sessions last week, so you should be familiar, but I'll just introduce in case there's someone new. My name is Zinia. I am a PhD student at the Indian Institute of Science, and I will be conducting these problem solving sessions for you for this NPTEL course of nuclear astrophysics. This is going to be a weekly thing with every Monday is supposed to be the session. As I just now mentioned to one of your friends, this Monday I had a prior thing, so I was not able to take the session. That's why it has been rescheduled to Saturday, but all the other sessions should take place on Monday as per the plan. So these sessions are going to be kind of like where we are going to discuss some and go over some of the things that you already studied in that week's lectures. I'll try to give you some more context or some more extra information about those lectures, and we'll also solve some quick questions which are similar enough to your assignment questions but not exactly your assignment questions. So this will help you to understand and solve your assignment questions better, but I will not be solving exactly your assignment questions because that is of course your job to do, and that will help you understand the course better. So this is in a forum where we can be interactive and we can discuss what all has been taught that week, and we can also learn, if you have any doubts like how your friend asked now about the color of the sun, we can also clear that up. So this is I think all the links of the Yeah, so very importantly, these sessions will be recorded and they will be put on YouTube. I think last week's link, etc., should have been communicated to you. The slides of the sessions are also, I am sharing it. So if you can't find any of it, I think it has been communicated to you by the PMRF team. In case you can't find it, it is also there on a page on my website where I'm collecting all the links together. So this is about all the housekeeping. So we can start the session. So I think so as I said, this is going to be a problem session that is mostly centered around your second week's lectures. I understand that you're more moving towards the third week. So let's just quickly recap what and all was covered in the second week lectures. You learned about how you can use other probes other than electromagnetic probes to look at the nucleosynthesis happening in the universe. So that included neutrinos, which are these very subatomic particles that don't interact much with matter but are produced in what are called beta decay processes. So when electrons and protons form neutrons, or when neutrons decay to protons and electrons, they emit a neutrino or an antineutrino. In fact, there are trillions of neutrinos passing through you right now, and you never know because they are very weakly interacting objects. So these help us to probe that actually these nuclear reactions are happening, because neutrinos only come in when nuclear reactions are happening. You also saw that gamma rays from, for example, the cosmic rays and all that can also help you probe the nucleosynthesis. Again, these are all, because this is a nuclear astrophysics course, we need to take care of both of the sides. So these are evidences that there is actually nuclear reactions happening in space. A common thing that we all have when we think about space is that it is empty, there is nothing happening there, but actually space is very active. There's a lot of processes that are going on in space, and nuclear reactions are like very central to the existence of stars. So speaking of stars, you should have learnt about the Hertzsprung-Russell diagram, which is commonly called the HR diagram, and a little bit about stellar evolution. And this problem solving session is going to be centered exactly about Hertzsprung-Russell diagram, and more importantly about the process of stellar evolution. So stars actually, they live and die in a certain way, and the stars' deaths are what results in one of all those beautiful pictures actually that we see from, for example, the telescope. Star births and star deaths are those, the resultants of which are what gives us those beautiful wallpapers that we set up, from JWST, or those black hole pictures, and all those exciting things actually comes from the same stellar evolution. So it's important to understand what are the different kinds of life stages, if I can call it that, that a star goes through. Apart from that, these are all things that might have been touched upon as I looked through your lectures: is Hubble expansion, the CMB or the cosmic microwave background, thermonuclear reactions, which we will touch upon a little bit when we talk about stellar evolution, and also cross sections and reaction rates. And I think the second half of this thermonuclear reaction, cross section and reaction rate will be explored more in your third week lecture, so we can discuss that on Monday. So yeah, as I said, these sessions happen every Monday. This is a rare case where I had to keep it on Saturday, so you will have another session day after tomorrow, which is as per the schedule, just to remind everyone. Okay, so let's start with stellar evolution. So as I said, stars have a life cycle. Oh, I'm so sorry. Hello. Yeah, so as I said, stars have a life cycle. Okay. Hello? Is someone unmuted? Can you please mute so there is no feedback? Or does someone want to say something? Hello? Excuse me, can you please mute if you're unmuted? Okay, yeah, thank you. Okay, so what was I saying? Right. So as I said, stars have a life cycle, and the birth and death of stars are what leads to very beautiful pictures like and supernovae and all those exciting physics that maybe we see in our science fiction movies. So this is just a quick picture to show you what are the different kinds of stellar evolution that happens, because not all stars follow the same kinds of evolution. This is very important. The main factor which determines how a star proceeds on its evolutionary track is its mass. So whether a star and whether a star is more massive or less massive kind of determines what it ends up as, and as you know, the star that we know the most about in our universe is our own sun. So usually in stellar physics, in astrophysics, what we do is we measure everything relative to our sun. So you will usually see things written as in terms of the sun's mass or the sun's radius or sun's luminosity, temperature, etc. You might have already started seeing it. We write it usually with M with a small dot in the side. So that means something relating to the sun, right? So here itself you can see that, of course, this is the birth of stars, and we'll be talking about this a little bit. So you can see molecular clouds are collapsing to form protostars, and from the protostars, depending on how massive the protostar has got, we get either low mass stars or massive stars. There's also a thing called brown dwarf, which I'll explain in a second. And you can see that all of these evolutionary paths depend on how massive the star is. So as I said, the main sort of determinant that determines how this, which path or which branch of stellar evolution a star will take, is given by the mass of the sun or mass of the particular star. So our sun, of course, will take this lower path, and we'll be talking about our sun in some detail. And more massive stars can, of course, end up even as black holes, but those are, extreme cases. Not all stars will end up as black holes. Some also end up as white dwarfs and neutron stars. And I am, of course, very interested in white dwarfs, neutron stars, and black holes, because these are the kind of research problems that I personally work on. So towards the end of today's class, I will also explain a little more about this class of objects and why they are exciting. But of course, every part of stellar evolution is exciting. You can see that in between the end stages and the beginning stages, there are also a bunch of in between stages, and there are all kinds of different physics which are involved. Okay. So today we will not be able to, of course, look at everything in a lot of detail, but my idea is to give you a glimpse or a flavor for what happens to a star generally as it moves through its life cycle, so that you get an idea, and then when you're interested, you can look up specific details according to what exactly it is you want to understand. Okay, so this is about stellar life cycle, and this has a lot of things, and hopefully we will, at the end of today's class, you will understand exactly this picture, maybe not in detail, but in some, to some extent at least. Okay, so first of all, when we are talking about a life cycle, we have to start at the very beginning. So how are stars born, right? Because at beginning of the universe itself, there are no stars. So I think we already discussed this to some extent in previous class, which is that stars are born in something called a stellar nursery or a nebula, which I think I showed you last week, the picture of pillars of creation. One of the first of the many pretty pictures that are going to come up in this talk is, that is the one of the first pictures that the James Webb Space Telescope released, was the pillars of creation, which are active star forming regions. So what are star forming regions? Essentially, we have these large clouds of gas and dust called molecular clouds, which are cold. And you know that from your high school physics, cold gases, they cold or hot is basically a measure of temperature, and temperature is a measure of kinetic energy, so how fast things are moving. So cold gases means their molecules, their atoms are slowly moving, which means eventually the gas clumps means it accumulates together and it gathers together, and we form these high density pockets. Eventually these clumps start colliding with each other instead of the molecules, and there is more and more, sorry, this is matter, not matter, but yeah, there is more and more matter which collects. And you know that when things get bigger, their gravity increases, and when gravity is bigger, things, get attracted to it more and more. So there's kind of like this runaway process, and as we accumulate more matter, the matter heats up, and we eventually end up with a protostar. So a protostar is not really a star. It's something like, which is, you can think of like a baby star. What happens is, because of the huge amount of matter in a small region, which is called a high density pocket, the protostar actually starts contracting due to the gravitational pull. So as the star contracts, it heats up. It's like your basic thermodynamics, right? When you have a gas in a piston and you compress it, the gas heats up. So that kind of same physics applies here. Basically, you're pushing all the matter together, causing it to heat up. And I think we discussed in great detail last week what exactly is the mechanism that holds stars like our sun together, which is nuclear fusion. So for a star to be born, we need those thermonuclear reactions, the nuclear fusion, particularly the fusion of hydrogen to form helium to start taking place. So the star has to, so there has to be enough matter so that it gets compressed and the star gets hot enough, the protostar gets hot enough that it starts fusing hydrogen to helium at its core. So this does not happen if there isn't enough matter, right? We need enough matter that forces the hydrogen fusion to start taking place. So when that doesn't happen, that is when we end up with what are called brown dwarfs. So brown dwarfs are failed stars where the matter has accumulated and they have formed these structures, but the gravitational energy was not enough to push the matter to start hydrogen fusion at the core. So there is no fusion reactions which are taking place, and usually these have masses less than around 0.08 solar mass. So again, as I said, in astrophysics we use most of our reference frames with respect to the sun, and whenever I put a dot like this, that refers to the some property of our own sun. So you can have a very quick check, is Jupiter a brown dwarf? And you can let me know next week what you find. But basically brown dwarfs are something which is in between a planet and a star. So Jupiter is not really a brown dwarf, and you can look up what are the differences between big planets like Jupiter and brown dwarfs when you look at that question. So essentially here you can see how nuclear physics comes in at every point in the star's life cycle, right? Even for a star to be born, nuclear fusion has to take place, which means the conditions have to be correct so that the nuclear fusion takes place. So imagine now we have enough mass that we are above this threshold, so we are not in the brown dwarf stage. In that case, we end up with what is called a main sequence star. So main sequence is basically the region where the star spends most of its life, which is where it is burning elements in its core and supporting itself against gravity. So always remember, whenever we talk about stars, the very first concept that I talked to you about was hydrostatic equilibrium, and that still holds, right? Hydrostatic equilibrium says that I am always going to have gravity that is going to try to crush my star, and I always need something to push back against gravity. So that's why, for example, nuclear reactions are important, because that helps you to push back against the star. So an interesting question which can come up in your mind is that if nuclear reactions aren't happening, for example, in brown dwarfs, how are they maintaining their their spherical shape, and how are they not collapsing? So that is very interesting, and the clue lies in the dwarf name, and they share some characteristics with white dwarfs, and that I will explain towards the end of the class after, if we get time. But yeah, essentially in all main sequence stars, what's happening is we have hydrogen, and that is being fused to helium, and some other nuclear reactions are happening. These reactions generate enough energy that they are able to balance gravity at outside the thing. Okay, so someone in the chat has asked, please provide the reference for this graph. Okay, I had provided references everywhere. I think I forgot this one, but this I think I got from the Wikipedia page. So let me just very quickly explain what you're seeing. So main sequence stars are usually uh, usually what is it? They're usually classified into different categories based on their spectral on the spectrum that you get. So spectrum is very important, which is spectrum is basically what is the light that you get from the sun. So you might wonder, right, how do I know that hydrogen is in the sun or helium is in the sun, or what are elements which are present in space, because no one has gone to the sun. So a spectrum is kind of like the fingerprint of an element, right? When I get a spectrum, I can identify that, okay, this element is there because these lines are getting absorbed. So what we expect is, you can see that in the spectrum, we expect that fully white light will come to us without any absorption lines. But these absorption lines indicate that, there has been some elements that are present which have actually absorbed that material. So you can see that people have marked hydrogen, helium, carbon, because where these absorption lines are occurring in the spectrum, that actually tells you what are the elements which are present in the star. So based on that and based on the temperatures, people classify stars into different categories. This was classified a long time ago ago. It is called the Harvard classification scheme, and it's based on, you know, the spectrum. So in the olden days, people did not have these computers and, you know, sort of these nice softwares to analyze. So what they would do is, once they get an image from a telescope, they would develop them on photographic plates, and there were teams of scientists who would sit down and look at the photographic plates and classify them. So this is how that Harvard spectral classification scheme came, because most of the scientists at Harvard, they were doing this, and actually it was a team of mostly women who were doing this, and they were called something like the Harvard computers. They were not called computers because they were using computers, but because they were the computers who were computing and classifying the elements. So about the reference, I will put it in the slide after the thing. I don't know how I missed it, but yeah, basically is a very famous, I think I got from Wikipedia page itself. So this is a very famous scheme. Our sun is a G type star. You can see here the spectral classes, the size, luminosity, temperature, all in this nice animation together. And you can see that there are stars which are much heavy, you know, more hotter than our sun, and there are stars which are very much colder than our sun. And usually brown dwarfs are, you know, even lower in temperature than these, because as I said, brown dwarfs don't have active nuclear reactions happening, so they are not very hot. You can see that the abundances go very low as we go to the very hot stars, and this is kind of consistent with the fact that, you know, the very big and very hot stars are very rare compared to the solar and subsolar kind of species. So this is the main sequence, and main sequence is actually sorry, main sequence is actually where the sun, or where a star will spend most of its lifetime. Now when does the main sequence end? The main sequence ends when the nuclear burning stops, right? So as I told you, the way that any star works, or for example, the way that any star works is through hydrostatic equilibrium. So we need gravity to balance pressure. Once that pressure is stopped being generated, then I no longer have anything to stabilize the star is just going to collapse. And this is when we get to our giant phases. Okay, so there are two kinds of evolutionary branches that stars follow depending on their mass. So if you look at the very first image I showed you, you can see that there are actually two branches. One is brown dwarf, of course, but we know brown dwarf is not really a star, so there's no longer any more evolution. The other two branches, you can see that depending on whether it's a low mass or a high mass star, it can follow either this branch or this branch, right? So both of these phases, you can see that the next branch is based on the giant phase, giant or supergiant phase. So as I said, every star has, you know, the way that it works is we need the matter to heat up at the core so that nuclear fusion starts taking place. And when that doesn't happen for hydrogen itself, that is when we get a brown dwarf. But in principle, this keeps happening at every stage of the star, right? For example, now our sun is burning hydrogen and forming helium. Then that means that helium in the core is keep on growing. But once the hydrogen runs out, the star is going to contract. And if the star has enough mass, then it will generate enough temperature that next helium will start burning, right? And helium burns to carbon, and then carbon burns to oxygen, oxygen burns to nitrogen, and so on. Oxygen burns to neon, and so on until we reach iron. And if you recall your elementary nuclear physics, you know that iron is the most stable element. So beyond iron, we don't have any more stable phases. Sorry, we don't have any more stable phases to form. So up to iron, we have this nuclear fusion which is possible in the star. But of course, that fusion will only happen if the star is able to reach high temperature. Sorry, give me a second. Hello? Hello. I hope you can hear me. Sorry, I had something stuck in my throat. So, right. So as I was saying, we have nuclear reactions which are happening in stars, and that is exactly what stabilizes them against gravity. So depending on the mass of the star, there are a sequence of nuclear reactions that can happen. Of course, every star starts with hydrogen burning. If the star, if this the mass of the object is not even high enough to start hydrogen burning, then we don't even have a star. We have something called a brown dwarf. Every star starts off with hydrogen burning, and if we cross that hurdle, then we get a star. Then of course, the further stages of nuclear burning is depending on the mass of the star. If the star is massive enough, really massive, then it will continue burning elements from hydrogen, helium, carbon, oxygen until iron. But if, like our sun, it is an intermediate mass star, then we see that all the elements are not burnt, but at some point, the star simply cannot get hot enough to go to the next stage of nuclear burning. Okay, so this is the very basic concept, and this is why there are different evolutionary tracks for low mass stars and massive stars. It is basically all depending on what the nuclear fusion is like at the center of the star. Okay, so I think we can. So once we are out of the main sequence phase, we are now in the giant phase. So essentially, as I said, every star starts off with a hydrogen burning core, and if its mass is somewhere less than 10 solar masses, then we see that the burning only happens up to around oxygen or carbon. It does not go beyond really oxygen or neon, and these are the stars which end up as white dwarfs. So these are essentially this branch of the stellar evolution, the lower branch, which you can see that end up as white dwarfs. So for these cases, you can see that something called a red giant is formed. Essentially what happens is that the hydrogen in the core is all burnt to helium, so now we have a helium core. So now of course gravity is not balancing the gravity is not balanced by the nuclear reactions happening in the core, so the star is collapsing, right? So as the star collapses, it heats up, and what happens is something called a mirror process, where the inner core starts collapsing, but the outer layers start expanding, and the star actually becomes 100 or very much higher, 100 times its previous size, and this is going to happen to our own sun as well, and this is why we call it a giant phase. So what happens is that in the core, the helium is used up, but there are actually hydrogen that is burning in the shell of the star, and that kind of phase is called a red giant phase. So this is the evolution for a less than 10 solar mass star. You can see that we have a main sequence star which is going to hydrogen burning, and then it fully gets converted to helium. There's a small hydrogen burning shell, but the rest of it has actually expanded, and sometimes the helium can also burn inside the core of the star if the star is massive enough. So again, this is a very important point that you should understand, is that every star has the capacity to go to a certain number of nuclear reactions. For a brown dwarf, there is no capacity to go to any reaction because its mass is not enough. So it's like mass is connected to gravity, but mass is also connected to nuclear reactions, because at the end of the day, everything has to balance each other out. Then only we get hydrostatic equilibrium. So this is a very important point. So depending on the mass of the star, we eventually get a certain sequence of nuclear reactions that can happen. So if the mass is below 10 solar mass, then hydrogen can burn. Then once the star collapses, maybe helium can burn if it's around 3 solar mass or higher. And then again it can collapse and carbon can burn, but there is not enough material to heat up the star again so that further reactions take place in the star. So this is a very important point. I hope you can all follow me. Please please mention in the chat if you have any questions about this point, this sequence of nuclear reactions happening in the star, because it's a very important point to understand. I'll just give you 2 minutes. Is there any question in the chat? I can check now. Can you go a bit slow? Okay, I'll go a little bit slower, Zainab. Thanks for that. So I'll just go a little bit slower. Okay, sure. Okay, so I'll just explain what I was saying just now. So we have just looked at two things right now, right? we are basically going to look at how a star evolves. And as we saw, the star evolves through two branches, right? There is a massive evolution and a low mass evolution, depending on whether the star is around 10 times solar mass or higher than that. So, the point is that to form a star and to continue a life of a star, it's all determined by what kind of nuclear reactions are happening in the star, because this is what determines eventually the hydrostatic equilibrium that happens in the star, right? So if the star is not able to even start the first nuclear reaction, which is your hydrogen burning, that is when we get a brown dwarf. That is a failed star. But depending on mass of the star, there can be more reactions that are happening. So every star starts off burning hydrogen and converting to helium, and if the star is massive enough, it can continue burning elements like helium, carbon. Helium is burning to carbon, carbon is burning to oxygen. By the way, when I say hydrogen is burning, I mean hydrogen fusion. So astrophysicists, when they say something is burning, they actually mean nuclear fusion. Elements are fusing to form new elements. So hydrogen burning means that hydrogen is fusing to form helium. After that, the next stage is helium burning, which is helium is burning to form carbon, and carbon is fuses to form oxygen, oxygen fuses to form neon, neon fuses to form magnesium, magnesium fuses to form silicon, and so on, and until it forms iron. So if you recall from nuclear physics, iron is the most stable element. So that means that there is no more fusion which is possible at that stage. And what we get is eventually another kinds of evolution, which I will talk about in a second. But the point is that after the first stage of evolution after the nuclear burning has, reached some kind of limit, so what we see is the outer layers of the star starts expanding. And this is what reaches a giant or a supergiant phase. So these are when the core of the star is, not having nuclear reactions, but the outer layers have expanded, and we get very big stars compared to their original size. So for heavy stars which are much more than 10 solar mass, we actually get supergiant stars. And if you've heard of the star Betelgeuse, that is actually a red supergiant star. So again, I don't want to explain every stage and what are red giants, because there are, in supergiant itself, there is red supergiant, blue supergiant, and so on. So I don't want to go into all those details. I just want to give you a flavor of what is happening. So the main thing to understand is that nuclear reactions determine what happens to the star, and there are two main kinds of nuclear or two main branches of stellar evolution that it can take, depending on how heavy the star is. Okay, so now comes the part where I was talking about, which is about all these beautiful images that we see, which are coming from the supernovae, right? So here you can see two kinds of pictures. One is of the ring nebula and the one is of the crab nebula, and these two look kind of similar in that they are both looking like, explosions of some kind, but actually their origins come from two different branches of this stellar evolution diagram. Okay, the ring nebula is a type of planetary nebula which you can see comes from the lower mass star evolution, whereas the crab nebula comes from this massive star evolution. So here you can clearly see the low mass versus high mass evolution, and these are actually called these result in what are called type 1 supernovae, and these are called type 2 supernovae. Here is actually the image that maybe I should have put in the previous slide, which is of all the element fusions that can happen in a star. So you can see that iron is the most stable, and then, of course, we have silicon, oxygen, neon, carbon, helium, and hydrogen. So every star starts off by burning hydrogen. Depending on its mass, it can contract and generate. If it can contract and generate enough temperature, then it starts to burn the further elements. So only if a star is very heavy, if it's very massive, can it go all the way to iron. So that's why there is a two kinds of evolution that's happening. For stars which are more massive than 10 solar mass, they can actually burn elements all the way up to even iron. But stars which are lower than 10 solar mass, they stop somewhere along this line. They can burn only up to carbon or up to neon or up to silicon or something, but they will not reach up to iron. And that is why there are two kinds of evolution. Is this clear to everybody? There's two kinds of evolution for low mass and high mass stars and the role of nuclear reactions. Please mention in the chat, and also about if my voice is breaking or something. Okay, just mention in the chat if there are any issues. I'm just moving forward because we have to do questions also. So, yeah, okay. Thanks everyone. So, so essentially, when I have a low mass star, the evolution stops somewhere in between where the nuclear fusion is able to go up to some element, but not the full way, and we get a red giant followed by a planetary nebula. Now, planetary is a wrong statement. You might think it has something to do with planets. It does not. It was named a long time ago before we really understood this process. But essentially, what happens is the star has exhausted all possibility of nuclear fusion. As I told you, nuclear reactions are very important because that's what helps stops the star from collapsing. Once a nuclear fusion has stopped, the star is going to collapse. It ejects out its outer layers in this planetary nebula, and that is what we see as this beautiful image, ring nebula. And then what is left behind is what is called a white dwarf. So that is one of the ways in which a star can end up. Now, if you are a more massive star, then you actually burn everything all the way up to iron, because you know you finish, if you exhaust hydrogen, your star contracts and you get helium. You get enough temperature to go to the next phase of burning, which is helium, and then you get enough temperature to go to carbon, and so on and so on, and you actually form shells like how it is seen here all the way up to iron. And then what happens is, once you reach iron, there is no more burning possible, even how much ever massive you are, because iron is very stable. You can't fuse it to form anything else without giving your own energy. So that's why you end up with a red supergiant phase, and you end up with something called a type 2 supernova, and this is what is the Crab nebula. So even though these pictures look similar, this is a planetary nebula and this is a type 2 supernova. So these are two different kinds of things, and they come from two different branches of the evolution. This comes from a light star's evolution, this comes from a heavy star's evolution. And this is a star which did not able to fuse elements all the way up to iron, but this is a star which was massive enough that its temperatures were able to rise enough to carry on fusion all the way up to iron also. So after the supernova, you can end up with either a black hole or a neutron star. So essentially, there are three kinds of objects that you can end up with if you are a star, which is a white dwarf, a neutron star, and a black hole. And these are kinds of called compact stars. So compact stars are basically the end stages of stellar evolution, and they are basically what's left behind after a star dies. Okay, and these are very interesting objects because they have very extreme properties, because they are extremely dense objects, right? So again, think back to hydrostatic equilibrium. I want pressure to balance gravity in my main sequence stars, and to my red giants to some extent, red giants, supergiants to some extent. What's happening is we have some nuclear fusion which is happening, and because of that, that's releasing energy to balance out the gravity of my star. In these objects, there is no more nuclear fusion which is happening, right? So in white dwarfs, what happens is there is this and actually I will explain the hydrostatic equilibrium, exactly how these objects are able to be stable towards the end of today's lecture. But the point is that these two objects are very interesting. They attain, hydrostatic equilibrium in a way that is different from, how our main sequence star attains. And of course, a black hole, which I'm sure you have all heard of, is what happens when there is nothing to prevent gravity from collapsing the star. And when the star is very heavy, no other mechanism can step in, and we see that the entire star collapses to a point, and that's what we call a black hole. So this is essentially the full picture of stellar evolution. As I said, I don't want to go into too many details because each and every point of this has something which is still unknown to us, right? These are all active fields of research. The point is that we roughly know that a star is born. When do we consider a star to be born? When it starts burning hydrogen. Some objects are not able to reach that. That's when we get brown dwarfs. Depending on how massive stars are, certain amount of nuclear reactions happen. If it's a low mass star like our sun, then all the nuclear reactions up to iron don't happen, and we end up with red giant followed by a planetary nebula stage, which ends up as a white dwarf. Whereas in a massive star phase, we end up as a red supergiant phase, because all the reactions up to iron happen. So at the end, once iron burning has happened, then the outer layers are expelled in a supernova, type 2 supernova, and then we end up with either a black hole or a neutron star. So this is essentially a broad picture of stellar evolution. I'll encourage you to go and read up on these objects if you have some interest in any of them, because each of these objects are interesting in their own right. So so now we can move on to HR diagram. So I think you have already learnt about the HR diagram, so I don't have to go into much detail, but essentially the HR diagram is a nice way to visualize all these different sort of objects that I said on a single scale. So here you can see that the axis is usually temperature and luminosity, and you can see again we are measuring with respect to the sun's luminosity. The sun's luminosity is set as 1, and you can see the sun is at this point in the HR diagram, and you can see that our and you can see that one thing that you have to be careful about is that the temperatures are always red in the opposite direction. So these are high temperatures, whereas these are low temperatures. We have to be careful because usually we might think it's the normal way. So luminosity increases in the up down direction, but temperature increases from right to left. Okay, and this is just a convention that has been followed enough that people do it. Of course, this is the most common way of plotting HR diagram, but you can see HR diagrams plotted with different things. For example, in a previous slide, I showed you a graph where the HR diagram was plotted along with the spectral class, because in the end of the day, all of these are related. So you can see that actually spectral class classification is based on temperature. So in that way, you can link, instead of temperature, you might see spectral class is plotted. You might see something called magnitude is plotted. So these are the things that don't get confused. Essentially a HR diagram is a luminosity temperature plot. So main sequence stars are along this part of the HR diagram. You can see that HR diagram is essentially an observational diagram, where when we observe things we put them in the HR diagram. You can see that essentially a lot of stars are in the main sequence, because that is the longest phase where hydrogen burning takes place over billions of years, right? Like our own sun is going to burn hydrogen for another 4 billion years, whereas the last part of evolution, where all that supernova and red giant phase, that all happens very fast, because that's essentially an unstable place where the nuclear reaction, the stable nuclear reactions of hydrogen fusion are not happening, and we get these very short lived phases. So actually if you look at the life cycle of stars, it's smaller stars live for way longer when compared to more massive stars. More massive stars actually live very short lives because their nuclear reactions are very fast and they have to go through a lot of stages. So you can see that the main sequence is this line, and you can see our sun is somewhere here. It is a G type star with a surface temperature of around 5700 Kelvin. You can see that your giants belong to this upper right part of this HR diagram. So they are not actually hotter, they are cooler, because as I said, temperature is always shown in the opposite way in an HR diagram. And your white dwarfs, they belong to this lower strip of the HR diagram. Okay, so I think you have already gone through this. So you can see that giants are here, super giants are here, and essentially these are a collection of stars, right? So when we want to look at the sun's evolution, right now the sun is here on the HR diagram, but if we had the technology to go 4 billion years in the future, we'll see the sun is somewhere here. And if we go a little further, 1 billion year after that, we'll see that the sun has ended up in the white dwarf phase. So stars actually move across this HR diagram as they go through their life cycle. So does this all make sense to you? Is there any questions up till now? Please put it in the chat or unmute if you have any questions. Okay, I don't see any questions, so I'm moving forward. But yeah, feel free to interrupt me in between if you have any questions as well. So this is not very, don't get worried by seeing all these big equations, but I just wanted to let you know. I just want you to at least see this. You will not be using this in this course, I think, but there are essentially 4 equations which are used to describe stellar structure. They are called the stellar structure equations. You've already kind of met one of them, which is hydrostatic equilibrium, which I keep talking about. And the reason is because that is the most central concept in stellar physics, is that pressure balances gravity. This is just a mathematical way of writing pressure balances gravity. And those of you who know Newtonian gravity, which I hope is all of you, you will be able to see that this is just an F equals ma, F equals gmm by r square kind of thing which is written in this way. The rest of them come from, mass conservation, energy conservation. This is coming from temperature and luminosity. So these are the main variables that we use to describe stars: pressure, mass, radius, temperature, and luminosity. And the others you don't have to worry about. You really won't be using these equations, but I just wanted you to know that there are some equations that we use to describe stars. And this is where those relationships, you can also infer kind of relationships between these quantities. I think in your lectures you spoke about a relationship between mass and luminosity, and these are kinds of ways in which how those quantities evolve. So I thought that it gets a bit abstract to talk about stellar structure. So I thought, let's take a specific case, which is the case of, again, the star that we know the most, which is our sun, and let's try to look into its future. So first I can show you, this is an artist's depiction of what happens to our sun. So as you recall, our sun belongs to which branch of this evolution? Can you just put it on the chat? Will our sun end up as a white dwarf? I mean, will it end up in the lower branch or the upper branch? Just answer in the chat. Lower branch, white dwarf, lower. Okay, good. You guys are paying attention. That's good. So yeah, our sun is not heavy enough to fuse elements all the way up to iron, so it will not end up forming a type 2 supernova. It's going to end up as a white dwarf, and this is an artist image of how that could happen. So our sun might be somewhere here. As you know, the lower branch, I'll just go back once more. The lower branch, you eventually end up as a red giant, which is where you expand a lot, and that is what you exactly see here, right? The red giant phase, and that is followed by, of course, a planetary nebula. So I have a homework for you, which is to find out why red giants are red. I already told you that in the red giant phase, what happens is that the core of the star collapses and its outer layers expand. And if you look at the HR diagram, you can see that red giants are on the cooler part of the temperature spectrum of the HR diagram as well. So putting that together along with Wien's law, which we discussed last time, you can actually think about why red giants are so-called red giants. So that will be your homework for today. You can go and try to reason with yourself why that is the case. So I'm sorry, I'm going back. So this is exactly the evolution of our sun on the HR diagram. So as I said, right now our sun is on the main sequence line, which is somewhere here. But as the sun evolves, it's going to move in its position from the HR diagram. You can see that around another, so it has started from here, it has come here. And it will keep staying here. Right now it's around 4.5 billion years since its birth. It'll keep staying here till around 12 giga years or 12 billion years, right? So you can see that the main sequence phase is around the longest phase of a star's life, because it spends around it lives for around 12 giga years. It spends almost 3/4 of its life only on the main sequence, and that's true for all stars. Along with this, you can see that once the star stops burning hydrogen and those giant phases happen, you can see that, as we expect, the star goes cooler on the temperature scale but bigger in size, so it's a bigger luminosity object, and this is the red giant phase. There is another giant phase which I have not talked about, which is called the asymptotic branch. So there are a lot of complicated nuclear physics happening, right, in the sense that there are flashes which happen in the star, which is where these violent eruptions happen where mass is lost in the star, and that's how it ejects its outer layers and so on. So helium flash happens, and eventually the outer layers are ejected completely, and that is a planetary nebula. That's where you get that beautiful explosion. And then what is left behind is a really small object which is called a white dwarf, and the white dwarf continues cooling because it has no more nuclear fusion which is available, so it just cools and cools and settles to the lower part of the spectrum. So I know this is a little difficult to see and imagine. So but this is essentially how a star moves on its main sequence. If we were a species that could live for 10 billion years, we would see our sun go through all these phases. Whether we would survive all these phases is a different story. So this is an artist's impression of how the sun would evolve in size. You can see that right now we are at 4.6 billion years. Of course, it started off as a molecular cloud which collapsed to a proto star, as I said before. So you can see that we are somewhere here right now from the molecular cloud stage. It's going to continue burning hydrogen until we reach the red giant phase. So you can see in the red giant phase we go from this size to actually a very huge size. So it's very difficult to imagine. So I've also put in a small video which we can watch, where they've actually made a small simulation or animation of what could happen, and that I think captures it the best of all. So we can just watch this video because it kind of captures all those different phases of stellar evolution that I was talking about. So let us just look at this video. So let's just So as I said, the sun is 4.5 billion years old, and that's what they have mentioned here. It started off in a molecular cloud where the gas collapsed to form the sun. So that's kind of the artist impression that they are giving here, and then eventually the solar system formed around it, but that's a different story. So these are all sort of animations that people have done to visualize how the sun could end up in the future. So based on, because as like just talking about the physics, nuclear physics, especially happening very far away, it might be difficult to imagine. So yeah, so this is, I can just skip ahead a little bit. Let's, yeah, I think now they'll start. So this is an artist's impression of a white dwarf. So you can see that this is a counter. If you can see that counter at the bottom, 4.7. So this is showing us how it will be few million years from now. You can see there's not much change. As I said, the hydrogen burning stage is the most stable stage in any star's life. It continues on with all the normal processes. These are solar flares, like what is happening in our star. This is 5 billion, 6 billion years from now. There is not much change, but it slowly starts expanding, right? So you can see that the habitable zone. So the habitable zone is basically, we are right now in the habitable zone because that if we were on Mars, the temperature is too cold. If we are on Venus, the temperature is too hot. We are in the correct space for the water to stay liquid on our surface. Water does not exist on any other planet in liquid form, or in any other form as far as we know, because this distance from the sun is not correct for the liquid water to exist. So habitable zone is defined as that. So you can see that in the future, as the sun starts expanding, it'll get closer to us, and the oceans will actually evaporate. So that is what they have shown you. So that is after 2 billion years or so, because now the age of the sun is shown to be 6 billion years. You can see that the sun keeps on expanding. Here you can see it's approaching the red giant phase. So you can see how exactly, yeah, so the sun shines 2700 times bigger. So it's actually getting bigger, and it also shines bigger because now it's a much bigger object. It's like having a small bulb and a big bulb, right? There is more area for the bulb to emit, so it will look like a very bright object even though it might be cooler. So you can see an artist simulation of how the sun could expand, and it becomes 250 times larger as it enters the red giant phase. That's a very huge number, and actually that's big enough that it could, I think, engulf Mercury and Venus and all that, and they mentioned that. So the sun cools down to around 2600 from 5800 Kelvin. That's what we saw on the HR diagram also, is that the sun moves to the right of the HR diagram, right, which is where the temperature is lower, but the luminosity is much higher, because now it's a big object. Even though it's a cool object, it's a big object. So you can see exactly the sun has fused all of the hydrogen in its core, and it finally enters the red giant phase. So this is exactly what is happening. And Mercury, Venus, and possibly Earth has been swallowed by the sun, because it's such a big object and it has like kind of engulfed all of us. Um, And now, the outer planets can take the role of what is Earth, the role that Earth is taking now. So this is kind of even more time, then Earth will definitely get engulfed, and we are left behind with only the white dwarf phase. So the planetary nebula has now happened, and all the outer layers are gone. That's this beautiful explosion that we see. So there will be something like a ring nebula happening in our own sun, and then after 12 billion years or so, we are left behind with just a white dwarf, which is this really small object that is glowing white in color. So the core of the sun remains as a white dwarf, and around it, if any planets are surviving, like the outer planets like Saturn or Uranus or something, they may stay bound, they may not stay bound, because now the gravity is not enough to keep these objects in orbit around the sun, right? uh, because, and this is how we get sort of lone planets which have escaped from their solar system and are not orbiting any fixed star in the in their system, and that's what we see lone exoplanets. So white dwarfs are extremely dense objects, and this is kind of what they have shown. I think we can stop here because I think the next part is about black dwarfs, which, yeah, so white dwarfs are really, really dense objects. They are very interesting. I'll try to talk more about them towards the end of today's lecture if we have time after solving questions. And yeah, white dwarfs basically lose energy very slowly, and they end up with something called a black dwarf. Black dwarfs are not observed yet because the white dwarf cooling time is so slow that there has not been any white dwarf which is completely cooled to a black dwarf yet, right? So you can see that we already have reached sort of 15 billion years. So, right now, so you can see that we need only 1 quadrillion years, which is a long, long time, which is when the white dwarf will completely cool down and cease to shine. That's when we call it a black dwarf. So that is the eventual fate of the sun. If you wait for, whatever is a quadrillion years, you will end up as a black dwarf. Okay, so that was a kind of a video to give you some context, because we've been talking about stellar evolution, but to look at the case which is the most familiar to us, which is our sun, we can see exactly what are the different phases of stellar evolution that happen. Of course, this is for the lower branch. In the upper branch, you see that the red giant phase itself doesn't happen. It's a supergiant phase which happens because all the nuclear reactions happen in that branch, and we end up with a supernova instead of planetary nebula. And beyond that, we can end up with either a neutron star or a black hole. So those details we can skip for now. So now we can do some questions. So I hope you guys will be interactive. So the first set of questions is all about the HR diagram. So you can see that there are some stars which have been marked on the HR diagram as A, B, C, D, and E. So each of these questions answer will be either one of these stars. So you please put your answers in the chat so that I can monitor them. So let's just look at some questions together. Okay, first question. These should be very easy, by the way, because I have explained everything already. Please put your answers in the chat. Okay. Yeah, I see most people saying D. Any more answers? Yeah, okay, D. Okay, good. I think everyone agrees that it is a D, and D is the correct answer. As you know, white dwarfs are very less luminous because they are very small. So you can think of luminosity as kind of like the power that something is emitting, right? A very big star is going to emit a lot. A very big star like a red giant is going to be very highly luminous, because if you have a very big bulb, it's going to emit a lot of light. If you have a small bulb, it's going to emit smaller amount of light. So that's the way you can think about radius and luminosity. Okay, and very good. Next, which of the group is the coolest star? Coolest in the sense of temperature, which is the coldest or coolest star? Please put your answers in the chat. Okay, someone says E, B, B, B. I see most people are saying B. Any other answers? Okay, I see that most of you have said B. That is the right answer. You can see that, as I said, you have to be very careful when you're reading HR diagrams. Here it's of course spectral class. Spectral class is the same as temperature, but it's usually the colder stars are here and the hotter stars are here. So temperature increases from right to left. So as you can see, the rightmost point is of course the star B. And any idea what star is B? Like what kind of star B would be? Like main sequence, giant, super giant, what kind of star it would be? Yeah, it would be something like a super giant star. Very good. Yes, super giant. Okay, okay, fine. You guys are listening. That's good. So the next question is, which one in the group is the most reddish main sequence star? So think about how color and temperature could be related. E, E, E. I see. I see people saying E. Okay, I see most people have said E. That is the right answer. As if you remember your last week's class on Wien's law, you know that temperature and wavelength are related inversely. So you know that red light has the longest wavelength. So in that case, we would expect red stars to be somewhat cooler in their evolution, and that's why we see the main. So of course, this middle branch is the main sequence branch. So when they say what is the most reddish main sequence star, what they're kind of asking is what is the coldest main sequence star we see in this marked questions, and that is of course E, right? So even though this is a reddish star as well based on temperature, we know that the main sequence branch is this one, so that's why you should be careful. Next question, which is the brightest star? I see a lot of people saying A. A. Any more answers? Okay, yeah. So, hello, sorry, was there a question? Hello, was there a question? Does anyone have a question? Well, okay, if no one has a question, you're all right. The answer is A. Basically, we are looking for the highest luminosity. Luminosity, of course, in HR diagram increases from up to down. So the which is at the topmost point, that is basically your most luminous and most brightest star. And which one in the group has the highest radius? This should be easy if you remember the classes of stars that we just now studied. So people are saying B. Any other answers? Others? What about your answer? B. I see one more B. Is absolute magnitude related to size? Okay, absolute magnitude, don't worry about it now. But it's more of, yeah, it's more related to luminosity rather than size. It's another way of classifying luminosity, actually. You just think about the evolution and how a star expands or contracts and how that tells you about the size. Okay, B. So yeah, I think most people agree that it's B, and that's correct, because this is essentially where the star has gone to main sequence and it is slowly expanding and is going. So if you remember in our sun's evolution, it was something like this, and that's exactly what's happening here. B. Which in the group has the lowest metallicity? So metallicity is essentially, yeah, how metallic a star is means, as you know, astronomers call anything which is beyond hydrogen or helium as metals. So that is what we mean by metallicity. Okay, I see some people saying D. Any other answers? Okay, the answer is actually A, because as you know, white dwarfs are actually, they need not be lowly metallic because they can have carbon or oxygen in their cores, whereas these are kind of the zero age main sequence stars, right? So here is where they have kind of started only. So they might not have had the opportunity to, because a star moves along this region in the HR diagram as it goes the main sequence. So it might not have had the opportunity to fuse. So how does a star become metallic? If hydrogen fuses to helium, fuses to carbon, and so on. So in the zero age, it might not have had the opportunity to um, burn to higher elements, and that's why it is lowly metallic. Okay. So this is the next question. Please put your answers in the chat. One hundred times faster. So which are the two quantities that you think play a role here? Think about that. So people, okay, so I see two answers. I see A and B. So any other answers? So here we have mass, and we also have this consumption of nuclear fuel, which comes into a specific physical quantity in the star. So think about it in terms of that. I think in your lecture you might have come across this. I might not have mentioned it right now. Any other answers in the chat? Please put further answers in the chat. Okay. I see C also. Okay, and I see that people are not agreeing. Please put more answers in the chat so we can have a majority. No, massive star, less time of what? I said a massive star lives shorter lifespan, right? Which means it consumes its nuclear fuel faster or slower. Its lifetime is shorter, but here we have not asked about lifetime. Here the question is about consumption of nuclear fuel. Huh. Okay. Okay, I think people are giving a lot of answers, so I will just reveal the answer. The answer is actually B. Do you guys know why? Have you learned what is the relation between mass and luminosity in your class? Maybe I should have put it on this slide, but yeah, have you guys learned what is the relation between mass and luminosity in this slide in your class? So if you remember, I can just put it here now. Do you recall this relation? Have you seen this relation in your class? Huh. So here, of course, 3.5 is a bit difficult. So luminosity is essentially how brightly the star burns, or you can think of it as how much nuclear energy it is giving out, right? If you that is kind of directly related. So yeah, so it is not exactly because of volume. That's a good guess, but the more of it is because luminosity and mass kind of have this relation. So if you take 10 to the power of 3.5 to be kind of like 10 to the power of 3, then you will get 1000 times. And as I said to your friend, more massive stars have shorter lifetime. So that means that everything happens way faster in a massive star, and that is what happens to um, in this case. So does everyone follow this question? Did you see this relation in your class? I think this should have been seen, right? I think I saw it in your lecture notes. So you should have seen it. So basically 10 to the power of 3.5, which is roughly 10 to the power of 3, if we approximate it, this 1000 times faster. Does everyone follow this? Please put yes or no. Okay. Yeah. So the point is that, yeah, maybe I should have said consume by approximately what factor. It's not a very correct, like a very, what is that, exact number. But yeah, this is how physics is done, right? Even L to the power m 3.5 is based on some observations which we have made, which is that massive stars are more luminous, and because they go through the reaction, so we are able to then infer that okay, they must be going through their reactions faster. And because we can measure populations, so as I showed you, massive star populations are very small. So from that you have to do statistical analysis, or you have to think about it. Why is massive star population small? One of the reasons could be that massive stars live very short lives. So when we look in the sky, we are not able to see as many of them, because many of them have already passed to their supernova stage. Whereas small stars, they live for long time spans, so when we are observing the sky, there is a good chance of seeing them. So this is the way that people can see, right? That's the way in which, because in astronomy and astrophysics, unlike the other sciences, we cannot go to a lab and design an experiment and do that test, right? We can't do a test to see how much a star will burn in its lifetime. We can only look at this population that we have now and look at its properties, and from that we can make some guesses. So this stellar evolution scheme I showed you, it's based on a lot of observations and a lot of input from nuclear physics people and astrophysics people working together and thinking, okay, this kind of model explain what are the population of stars we see, and what is the kind of range of the masses that we see, luminosities that we see, objects that we see. And so far it has been explaining it pretty well, and that's how we come at stellar evolution models. So there is no F equals ma kind of postulate that we can start from and derive. We have to kind of rely on observations. That's why those missions that I mentioned to you yesterday, sending telescopes and probes to the sky, is very important. And now hopefully through this course you will also pick up certain tools to help you also estimate some properties easily. So you already know one thing, which is that if a star looks redder, it's cooler, and if a star looks bluer, it's uh, hotter. So that is one very quick check. So there will be other things that you will kind of pick up. So L proportional to M 3.5 is like a very approximate law that comes from HR diagrams. Again, we see that the luminosity, and if we draw a line between the luminosity and the mass in the HR diagram, it has a slope of 3.5, for example. Those kinds of things is how these elements are made, and that's how you that. And now we have some sort of sophisticated simulations where we can simulate stellar evolution, and that is some of the work which I do. Even then there are a lot of unknowns. We are not able to fully understand what happens in the supernova phase or the planetary nebula phase or even in the red giant phase. So each of those phases, which I quickly mentioned in the beginning of the lecture, they each have their own research problems and research things which are going on. So it's a very rich field, stellar evolution, and we have to rely on observations to learn more about it. So the next question. Okay, again, this should be doable by you if you know some basic thermodynamics. Again, this is a scaling question, right? So scaling means I'm not worried about I'm a little worried about it, but yeah. You just think about how the powers of radius and temperature and luminosity are all related. And here's something related to your black body physics comes in. So just think about it like that. Uh, can you in chat put in which law you can use here to find out this answer? If anyone knows immediately the answer. Stephen's law. Okay, good. So you know what law it is. So now just put in the calculation and let me know the answer. If you want the luminosity, no, I think you don't have to need the solar luminosity. Here all the quantities are given to you. So you can just calculate it. I can also calculate it side by side to ensure the answer. Okay, I see people are saying C. One person has said C. Everyone else? Do you know Stephen's law? So I think someone wrote a mail to me recently and asking about some of the prerequisites of the course, kind of. So I'll just take this opportunity to say Stephen's law, Wien's law. These are all related to your thermodynamics and black body physics especially. And because stars are modeled as black bodies, one of the simplest kind of mathematical calculations you can do is based on black body physics. So if you are not very familiar or very comfortable with black body systems, I would suggest that you just go and look at it. So it is basically from your class 12, if I remember correctly, you have a chapter on this radiation and all that. So you can look at this black body physics. In that you will have, Planck's law, Stephen Boltzmann law, which is what we are using now, and also the Wien's displacement law. Of this, these two are very important because Stephen Boltzmann law helps you to relate radius, temperature, and luminosity. Luminosity is basically like release of energy, right? So energy essentially. And your Wien's law, as I said, helps you to determine color and temperature, because color is related to wavelength, and you know that wavelength and temperature are directly related for a black body spectrum. So I would suggest that if you are not very comfortable to follow the course and do the questions more, you can go back and brush up on those concepts, especially because that is very important. So I don't see any other answers in the chat. Can you please verify if C is correct, C is wrong, any other answers? There are lots of options on the screen. You can do it on a calculator if it's faster. But yeah, I want one or two more answers before I move to the answer. Please share your answers in the chat. Watts to Ergs per. Okay. So I'll just put the relation. So 1 joule is basically, I think, 10 to the 7, if I remember. Yeah, 10 power 7 ergs. I'll put it in the, yeah, maybe I'll put it in the slide also after this. Yeah, I think that should help you. So yeah, in astrophysics, the units are always very non-standard. As I said, we measure everything in terms of the sun, and sometimes sometimes Kelvin is usually used for temperature. So those kinds of things are there. Mostly everything is measured with respect to sun. So usually we'll see solar luminosity, and the sun's energy is, I'm not very good with remembering numbers, but I think it's around 4 10 power 33 ergs per second or something like that. So yeah, people usually in astrophysics you'll see everything measured with respect to sun. So yeah, 1 joule is 10 power 7 ergs. Answers in the chat, anyone? I see only Anamika has answered, that's why. Okay, I see one more C. Other people, are you solving? Okay, one more C. Anyone else? B. Okay, I see a different answer now. Rest of you, please put your answer in the chat and then I'll move to the answer. I hope you're all solving. This is a straightforward formula substitution. It should not take you much time. But I will give you 1 more minute. Okay, I think we can move to the answer. I hope those of you who haven't solved, please continue and check if your answer is correct. The answer is actually C. I think many of you got C. And I will just write the formula here in case people don't know. Of course, energy or luminosity is, you can think of Stephen Boltzmann's law. The luminosity is some factors proportional to to some t to the 4 r square, and then there is a constant of some kind, 5.67 kind of constant, and here 1 joule is 10 to the power of minus 7, sorry, 10 to the 7. So if you put all that together, you will get 6.66 as the answer. So I hope whoever would be, just go back and check your calculation. So what is the anticipated future of the sun? Again, this should be a very easy question. Sorry, because we saw a whole video about it. So please write its the answer in the chat. B, others, B. Okay, I see that you all watched the video. That's good. So of course, as we saw in the video, the sun will become a red giant when it starts burning helium in the core. The outer layers will expand. Eventually, they'll cool down. It becomes a red giant, and then eventually it expels the outer layers in a planetary nebula, and we end up with a white dwarf at the core. So finally, which of the following cannot be described using a Maxwell-Boltzmann distribution? So this, I don't know, you might not know. This has a little bit to do with something I discussed in a previous week's lecture, one of the questions which I did last week. So yeah, just try to answer this. And this will tie us to the last part of what I'm going to discuss today very nicely. So yeah, please put your answers in the chat. Okay, I see someone has said E. 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 Any more people? E. I see more E. Okay, I think everyone agrees. Very good. So you know the right answer. The answer is white dwarfs. I explained this kind of last week, and I explained it based on this relation, which I think many of you were able to identify correctly last week. This is the de Broglie relation, which is between the wavelength and momentum, and it essentially highlights the dual nature of matter, right? Matter has not only a particle nature, but it also has a wave nature, all matter. And this is basically the limit of where quantum mechanics becomes important. So I told you in the beginning, how are brown dwarfs, white dwarfs, neutron stars, etc., how are they held in hydrostatic equilibrium? Because so far, whatever hydrostatic equilibrium I've described, it has been based on nuclear pressure balancing gravity. But we know that in brown dwarfs, in white dwarfs, in neutron stars, there is no nuclear reactions which are happening. So what balances the star against gravity? So it turns out that there is quantum mechanics at play, and as I showed and as I said and as you saw in the video also, white dwarfs are really dense objects. right? So a typical white dwarf has something like mass of the sun contained within just the radius of the earth. So it is a very small, very densely, closely packed object. So what that means is that the atoms are so, or the, yeah, the electrons in a white dwarf, they are so closely packed together that their packing is of the same length as their wavelength, right? So in normal life, what happens is, of course, me and you and the ball we throw and the car we go in, they all have a wavelength. But the wavelength is so small that our waves don't really interact with each other and we can get away with just using Newtonian mechanics. But when we go to very tightly packed structures, the waves actually overlap and they cause all kinds of quantum effects, and that's why quantum mechanics become important. So actually, the way that white dwarfs and brown dwarfs and neutron stars are stabilized against gravity has a lot to do with quantum mechanics, and it has a lot to do with this particular relation. So that kind of brings me to the last part of what I wanted to discuss with you. So after the questions, so this part, I will warn you, is going to be, I mean, we have around 20 minutes before I close the session. So I want to very quickly tell you about hydrostatic equilibrium in compact stars. So as I said before, compact stars includes white dwarfs, neutron stars and black holes. Of course, in black holes there is no concept of hydrostatic equilibrium, because black hole is when the star is so massive that nothing can balance it against gravity and it has completely collapsed. So more of white dwarfs and neutron stars. And as I said in the previous week's lecture, white dwarfs and neutron stars are very near and dear to me, because these are exactly the things which I work on. So I just wanted to use this question kind of as an opportunity to talk a little bit about hydrostatic equilibrium in compact stars. This is something which is a little off tangent from your course, so it's okay if you don't follow everything which I'm going to say right now. It's fine. I want you to use this as an opportunity that if this looks interesting to you, to go out and read more about it, because this is really fascinating part of physics, and I am of course biased because I work in this field. But yeah, so I have put an image here. Can any of you identify what this image represents? Because this is kind of central to why hydrostatic equilibrium works in compact stars. If you can find out what this image represents, please put it in the chat. And I think you should know this from your school physics kind of. Okay, someone says spin. Good, that's kind of what it is. But yeah, not really spin. This shows a certain law. But yeah, spin is of course playing a role, and that's why there are orange and blue arrows. Any other guesses as to what this is? Okay. Okay. Any other guesses? Keep guessing. Again, this part is like kind of, it's not, I don't know if this will come up in your course, so I think this is just for some extra information for those who are interested. Okay, so I see off-bow principle, Pauli law, etc. coming up. So I think you are all on the right track. This is actually the Pauli exclusion principle. So have you all heard of the Pauli exclusion principle in your high school physics or chemistry? Yes or no? Yeah, okay. You have heard of Pauli exclusion principle, right? Pauli exclusion principle basically is a very fancy way of saying that electrons don't like being together, right? Electrons don't like being pushed together, because only electrons, if they have different enough, will they belong to the same orbital. So you know that when you write your electronic configuration of atoms, you can't write two electrons with the same spin in the same orbital, because they don't like being together and they will not be together. So instead, only if two different kinds of electrons are there in an orbit, then only we can fill that orbital, right? So basically, if you have too many of the same kinds of electrons and you push them together, they resist. They don't like being together. And that's exactly what happens in a white dwarf or a neutron star, is that all that weird quantum mechanics I told you before comes in, and this is essentially something that comes up due to quantum mechanics. If any of you, have taken physics courses in And specifically if you've taken statistical mechanics courses, you will come across this in great detail. I don't want to go into it, but the point is that it all comes down to electrons don't like being together. Electrons are actually a type of object called fermions, and fermions really don't like being together, and that's why they obey something called the Pauli exclusion principle. So, as I said, white dwarfs are compact stars which are formed towards the end of star's life, starting off with masses less than 10 solar mass. They are supported against gravitational collapse by something called the degeneracy pressure of their constituent electrons. So, this degeneracy pressure exactly comes from what I said, which is that, as you try to push electrons together, they push back. Because of Pauli exclusion, they say, hey, I don't want to be pushed together, I'm going to push back, and that's what comes into the white dwarf. So, as I said in my previous lecture, I guess hydrostatic equilibrium, I said when a star exists, it's always being pushed by gravity. So we need something to push back. Till now we had nuclear reactions to push back. Now what happens is the Pauli exclusion principle pushes back. So now the question comes, why Pauli exclusion comes in and the white dwarf stage but not in the main sequence stage? It all has to do with this relation, right? The density of the object is different. In our sun, the objects are not so densely packed as they are in a white dwarf, where a white dwarf has so much matter pressed to a very small size. They are also closely packed that all the quantum effects start becoming important because the wavelength is of the same order as the packing fraction. Again, if you can't follow this, don't worry about it. I just think it's very interesting, and those of you who are interested can look into it more. So here is an image of the Sirius binary star system. So most of the stars in our universe are in binaries, which means that there are two stars which are orbiting each other. Our sun is one of the very rare isolated stars where it doesn't have a companion. In this picture, Sirius is of course a very bright star which is near us. This small dot that you see where an arrow is placed, that is actually the white dwarf, which is called Sirius B. So white dwarfs are really, really small when you think of them, and they have so much mass contained within them. That's why their densities are so high. And if you've heard about white dwarfs, you've heard about something called the Chandrasekhar limit. Okay, you know that all white dwarfs have something called a maximum mass which they can support, which is called the Chandrasekhar limit. It was derived by Subramaniam Chandrasekhar all the way back in 1930, and it actually won him the Nobel Prize in Physics in the 1980s, I think 1983 or something. So this is a very fundamental limit. There is a very beautiful way of deriving it, and yeah, this is basically a zeroth order explanation of what the how our white dwarfs held together. So essentially fermions, as I said, you don't have to worry about all this, but the important thing to understand is that fermions obey the Pauli exclusion principle. Again, those of you who come from physics backgrounds or have taken statistical physics course, you will recognize these terms like half integral spin and this occupation number diagram. If you don't, it doesn't matter. But the point is that even at zero temperature, because the fermions have this Pauli exclusion principle, or the electrons have Pauli exclusion principle, as I push them together, they push back and they provide this pressure which is called the degeneracy pressure, and that is why my white dwarf remains stable. Okay, so even though the gravity continues to push it, the electrons can push back, but there is a limit up to which the electrons can push back, and that is the Chandrasekhar limit. So if you want to derive the Chandrasekhar limit, this is Chandrasekhar's original paper. You can see it was published in 1935. Basically, you know that there is a cosmic speed limit, right? So as you push the electrons together, they get more and more energetic, and when something gets more energetic, as you know, temperature increases, right? You can think of it kind of like that. Energy is related to temperature, temperature is related to velocity or something like that. So in the end of the day, what you see is that the velocity gets so high that you reach the speed of light, and that is exactly when you reach the Chandrasekhar limit. Now I know this is a little bit higher in scope than you can appreciate, but I will just say that if you are interested in this kind of thing and you have some background of statistical physics, I would encourage you to look up this paper called Compact Stars for Undergraduates. If you have some coding kind of experience where you can solve differential equations and so on, you can very easily write up a simple code to find out the Chandrasekhar limit from first principles, and you can use the stellar structure equations that I showed previously. If you are interested in that kind of thing, please write to me. I can provide you with more resources to read about this kind of thing. So there is this nice quote by David Tong, because it kind of encapsulates the richness of compact star physics in general. Because as you see that there's a lot of physics which goes on in understanding compact stars, right? As I said, the de Broglie principle and quantum mechanics comes in. At the same time, there's gravity that comes in. There's a speed of light coming in somehow. Again, I've not explained this in great detail because it's a little complicated. But basically, there are two or three kinds of different physics which come into this one very special object, and that is why white dwarfs are really interesting to study from a theoretical perspective. Okay, so finally, I would like to ask, why is there no new Chandrasekhar limit for neutron stars? So in the beginning, the very beginning, I guess before all this, if I go to the beginning of our slides, you saw that we have three kinds of compact stars, right? We have white dwarfs, we have neutron stars, and we have black holes, depending on how heavy the star is. Our sun, as I said, does not burn all the elements to ions, so it only ends up as a white dwarf. Other stars can go through the full nuclear reaction process and end up after type to supernova as neutron star. And if the star is so heavy, even after burning all the reactions, even after going through supernova, that nothing can stabilize it, not even all this quantum weirdness I'm talking about, then it finally collapses to a black hole. And then there is no hope because gravity is so strong, right? So eventually gravity wins. But if the star's mass is not so high, then we can manage by forming white dwarf and neutron star. So the question remains that for white dwarfs we have a Chandrasekhar limit, and I told you a very quick and maybe little bit complicated way of understanding the Chandrasekhar limit. But the point is that, as I said, Chandrasekhar derived his limit all the way back in 1930, right? And he won Nobel Prize in 1980. So there has not been in the whatever nearly 100 years since then, we have not had a similar limit for the neutron star, even though they have lot of the same physics. So why is that? So the reason for that is, and I'll just skip ahead back to where we were. Let's just go. So the reason for that is that neutron stars have something like extra. So they have something that is the neutron degeneracy pressure. So neutrons are just like electrons, they are also fermions, and they hate being pushed together. So neutron stars are actually even more dense than white dwarfs. So they are very, very extreme. So you might think that, black holes are the most extreme objects in the universe, and that is to some extent true. But black holes are easy to understand if you know some, complicated physics. But for neutron stars, even how much ever physics we still do not understand them. Neutron stars are a very active field of research in current astrophysics. The reason for that is that something called the equation of state is not well understood in neutron stars. So to explain the concept of equation of state, I'll just say very simply, right? Equation of state is basically what stuff is made of. So the ground has a certain equation of state. That's why I'm able to stand on it. If I go and stand on surface of water, I'll just sink down, right? That is because the equation of state of water is not the same as the equation of state of ground. The equation of state of air is different. So every object is made up of something and it has certain properties. If I stand on the ground, it gives me a pressure back, and that's why I'm able to stand. If I stand on water, it does not give me a pressure back, right? That's why I'm not able to stand on the surface of water. So like this, we know what things are made of, and we know how to understand what happens to them. But with neutron stars, they are so dense and they are so extreme that we really don't know what they are made of and what is happening inside them at all. So just to give you some idea of the numbers, typical neutron star has something like the mass of the sun. So imagine the weight of the sun, the entire mass of the sun contained within just 10 kilometers. So 10 kilometers will be like smaller than maybe just the area you live in, right? Just your area and maybe your school and the neighboring shops or something like that. Within that radius you have the entire mass of the sun. It is so very dense that a teaspoon of neutron star matter could weigh as much as many skyscrapers and planets put together or something like that. So there's some, it's a very extreme object, and because of this, physicists are not able to understand what it's made of. What is its equation of state? Is it more like water? Is it more like ground? I really don't know. So there are these things called strong nuclear interactions which makes the equation of state uncertain, and because of this I don't have a Chandrasekhar limit for neutron stars. So white dwarfs in that sense are simple because they behave kind of like metals. So we know that their equation of state is kind of like metals, and that's why Chandrasekhar was able to easily derive a limit, not easily derive a limit, but straightforward limit calculation could happen. But in neutron stars, we really don't know. So if you recall your again your school physics, when you learnt about atoms you would have learnt about something called the nuclear density, right? You know that the density inside every nucleus, regardless of what element it is the same, because you get something like rho is, I think, m by r. So m is proportional to a and r cube is also proportional to a. So we find you end up with a constant, and that constant is 2.7 times 10 power 14 grams per cc or kilogram per meter cube, one of those grams per cc. So it's very, very dense, right, inside an atom. In a neutron star, it actually goes many times that. So instead of nuclear saturation density, it goes many, many multiples of that density. And because of that, we really don't know how matter behaves. We know up to what we see on earth, and what we see on earth is just atoms and elements around us. We don't know what happens when you pack so much matter inside a space. We can't do that. Again, as I said, one of the shortgivings or shortcomings of astrophysics is we cannot go and build a neutron star in a lab and do experiments on it. So we are reliant on doing, nuclear physics, like what you're doing, nuclear astrophysics, and kind of learning about it in that way. So yeah, so this is a big unknown and this is an open problem. So I just want to leave you with this because this is actually a recent paper which I made, which I wrote with my supervisor and collaborator, about how different equations of state can lead to different mass radius relationships. Again, this is way beyond what this course is offering, but I just wanted to give you a flavor for how compact star physics still has a lot of open problems. And stellar evolution in general has a lot of open problems and a lot of interesting physics. So I'll just go back to the diagram I showed you in the beginning. As I said, it's very nice to look at this diagram. It looks like we have it all figured out, but each and every point or each and every stage on this diagram has its own questions and confusions which come in. So I have just introduced you to some of the open questions that come in when we look at neutron stars particularly. But as I said, there's a lot of these stages that we still don't understand, and the hope is that people like you who are interested in astrophysics will continue to read up and take this as a career and join us in understanding more about these stars and their evolutionary cycles. And it tells us a lot about how we came to be as well, and help us make those nice kind of movies that I showed you regarding the sun's life. So yeah, that's what I want to leave you with, is about hydrostatic equilibrium achieved in objects which are not on the main sequence, and how Pauli exclusion principle comes in. So I am once again going to end with this particular diagram, which I think I showed in the first lecture as well. So I think now you're in a position where you understand a lot of these sort of labels: dying low mass stars, dying high mass stars, white dwarf supernovae, emerging neutron stars. So we maybe didn't talk about these, but we definitely talked about dying low mass stars and dying high mass stars. Dying low mass stars essentially means planetary nebulae. Dying high mass stars means supernovae. And that's why people, there's this famous quote that we are all made of star stuff. And that's because if you see, a lot of the elements come from these two processes: dying high low mass stars and dying high mass stars. So for example, gold, which we all wear, all the gold in the universe comes from type 2 supernovae, and that is a known fact, because that is where as I said, inside the star only up to iron we can synthesize. So that's a very interesting question, is that where do the elements which are higher than iron come from then? They are not made inside the stars. So the answer is they come when stars die. And that's why the the quote of "we are all made of star stuff" should be slightly modified of "we are all made of dead star stuff," for the main part. So yeah, I mean I'm going to keep flashing this image because I think being a nuclear astrophysics course, understanding the periodic table with an eye for the universe is very important for your course in general. So yeah, hopefully as the weeks go on, you will be very well acquainted with this image and the processes inside it. And yeah, I'll leave our lecture for today here. I think I don't see any questions in the chat, so I don't think there's anything much. If you didn't follow the last part about compact stars, don't worry. It was a little rushed, and of course, it's not very relevant for your course, so you don't have to worry about it. I just want to give you a flavor of the field so that if any of you are interested or have some background in statistical physics, you can, you know, keep looking at it if you're interested. And of course, write to me if you have any other concerns or questions. So I'll just flash the first slide again. So again, this is my email ID, and this is the site where you can find all of the sort of links and videos and slides and everything which is made. Of course, they will also be shared to you by the NPTEL team. So yeah, keep an eye out for all of them, and I can share this in the chat also. Right. Yeah, so I've also shared the link in the chat. If you told you have, if you can't find any of the lectures or something, just save this link. I'll be updating it. I'll upload this session and the slides for the session by tomorrow. And as I mentioned, this is a anomalous week. Like, this week I had Monday some other commitment, that's why I was not able to take the class. But rest of the weeks we will have it on Monday only. So on 12th, that is day after tomorrow, we will be having the week 3 problem solving session. So yeah, don't miss that session, please join. And yeah, if you have any questions in the meantime, put it on the discussion forums or mail me. Or yeah, actually it will be the best if you bring it up during the session itself, because these 2 hours are actually for that very purpose. So I think with that we can close the session. So any other questions or comments from anyone? Okay, someone has asked a question. If black hole is the final stage and no reaction takes place, then how does the black hole evaporate? Am I asking the right question? Okay, you're asking the right question. So yes, black holes do evaporate through something called Hawking radiation, but that does not have anything to do with nuclear reactions. There is no nucleosynthesis happening inside black holes. There are some other processes which can happen which are related to Hawking radiation, and they are more to do with quantum mechanics. So I don't want to go into the details, but yeah, the simple answer to the question is that nuclear reactions are not the culprit. And black holes, see, as I said, white dwarfs, as you saw in the video, I said white dwarfs are the final stage, but you saw that white dwarfs eventually cool to black dwarfs. It's just that the time scale is so long that we have not seen a black dwarf yet. Similarly, black hole evaporation, it takes over such time scales that yeah, I mean, Hawking radiation, it's a little complicated. Let's not go into details. But yeah, when I say final stage, I don't mean it is necessarily static, right? They still can evolve. They don't undergo evolutions like through, red giant or something like that. They undergo evolutions by cooling down and evaporating or something like that. So Hawking radiation is not through nucleosynthesis, it's through another process which, yeah, which is more to do with this vacuum, field excitations and all that. We don't have to go into it. So the simple answer is that it's not because of nuclear physics. That's so don't worry about it for this particular course. You can worry about it when you take a GR course or something. So yeah, I think there are no other questions in the chat. So let's finish up this session. And yeah, so don't forget, Monday is the next session. So please join then also. Okay. So yeah, thanks everyone. So I'm going to stop my screen. Yeah, thanks everyone. Enjoy the rest of your weekend. And thanks for joining on a weekend also.